Okay, so now we're going to prove basically what you could consider a generalized intermediate value theorem. And the statement is basically that a continuous function on a connected set, the image of a connected set under a continuous function is connected. Or in other words, continuous functions preserve connectedness. So let me just state the theorem. So let S and S star be metric spaces and F from S to S star is continuous. Then if E is connected, so is F of E as a subset of S star. Okay? So the proof is actually very simple, and it really ties together some of the concepts that we've been talking about nicely, I think. So suppose F of E is disconnected, i.e. there exists U1 and U2 disconnecting F of E. And so when I say U1 and U2 disconnect F of E, I mean that they satisfy the hypotheses of the definition of what it means for a set to be disconnected, right? So the whole thing with like they're disjoint, and then F of E, the intersection with U1 and U2, you know, the intersections union to F of E and so on, right? All of that stuff. So then we claim, this is very simple, that F inverse of U1 and F inverse of U2 disconnect E, right? So that would contradict our assumption that E is connected, okay? So why is this the case? This is because, right, well, okay. So, okay. First of all, so, well, okay, let's just go through, let's go carefully. We have F inverse of U1 intersect E intersect F inverse U2 intersect E is the empty set because no X in E can have F of X in U1 and F of X in U2 at once, right? This is because U1 and U2, we assumed, disconnected F of E, so they're disjoint, right? So if X was in both inverse images, that would mean F of X would have to be in U1 and F of X would have to be in U2, right? And that's not allowed, okay? So that's impossible. So this is, so they're disjoint at least. They separate E into two disjoint pieces. And then also so for any X in E, either F of X is in U1 or F of X is in U2, right? It has to be in at least one of them because U1 and U2 cover the original set, or cover the original set F of E, right? So U1 and U2 cover F of E. So F of X is in F of E. That means it has to be in one of the two sets. Then that means that X is in F inverse of U1 or X is in F inverse of U2 accordingly, right? So this shows that F inverse of U1 and F inverse U2 cover E itself, right? Lastly, F inverse of U1 and F inverse of U2 are non-empty because U1 and U2 are non-empty. Okay, I ran out of room. But F inverse of U1 and F inverse of U2 are non-empty because U1 and U2 are non-empty. So if there's a point in U1, that's only possible because it comes from a point in E, right? So, and then that point in E has to be an F inverse of U1. And similarly, if there's a point in U2, that has to be the value of F at some point in E, but then that point in E would have to be an F inverse of U2, right? So they're both non-empty. So all the hypotheses are satisfied. So there you go. If F of E is disconnected, you can use those sets and take their inverse images and disconnect E itself, okay? So the image of any connected set is connected. So as a corollary, right? So let F be a continuous function from a metric space to the real line, right? E continuous and E connected. Then F of E is an interval in R. In particular, F has the intermediate value property. So they don't really elaborate on this in the book, but clearly, if if S is a subset of R, okay, actually S is not a good letter to use here. Let's say A, I don't know. If A is a subset of R and A and B are in A, but C is not in A, where A is less than C, less than B, then negative infinity C and C infinity disconnect A. So intervals are the only connected sets in R. So this suffices to really prove the corollary now, right? Because the corollary, by the previous theorem, we know that F of E, in this situation, F of E would have to be connected. And then I just showed that the only connected sets are intervals. So that means that F of E is an interval, right? And of course, then that means that F of E has the that F has the intermediate value property. Yeah, you can think of this, even this is still more generalized than the version of the intermediate value theorem that we actually proved, because the version we proved was for functions from R to R. But this version of the intermediate value theorem actually works for functions from any metric space to R. So that's kind of nice. Anyway, so I think this is actually a really beautiful illustration of the power of topological concepts in general, that we made what are actually, by all rights, very simple definitions, right? No epsilons or deltas were really involved for the most part. Well, I guess there was some epsilons and there was epsilons involved in the definition of open sets. But beyond that point, the concepts of connectedness and closed sets and a lot of these things were relatively simple. And we were able to kind of, use them to furnish these very elegant proofs of actually more powerful statements than things like the intermediate value theorem and the closed the stuff about continuous functions on closed intervals, right? All of that stuff might have seemed kind of opaque before, but I hope that this topological perspective shows you how there's actually a very deep and kind of a elegant pattern to why these things are true, and there's sort of a higher perspective on it. So anyway, I think there will be one more video for this lecture, and that will be about path connectedness. So